Assalamualaikum warahmatullahi wabarakatuh. Please recite doa first. So today we are going to continue on multiple integral. Let's proceed to double integrals in polar coordinate first. Okay, now let's take a look on region A and also region B. If we want to evaluate this region, which is R, and also this one, R, it is quite complicated if we are using the rectangular coordinate. That is why we need the polar coordinate to evaluate double integral of this region. So in polar coordinate, we need three important things, which are r square is equal to x square plus y square, x is equal to r cos theta, and also y is equal to r sin theta. Okay, this one is from the Pythagoras theorem. So our value x here is r cos theta. This one is y sin theta. Okay, now let's proceed to simple polar regions. A simple polar region in a polar coordinate system is a region that is enclosed between two rays, which are theta is equal to A. Okay, this one, theta is equal to A, and also theta is equal to B. Okay, and two continuous polar curves, which are R1 and R2. Okay, this one is R1 and R2. And this polar curve satisfy the following conditions. The first one is A is equal or less than B, B minus A is less or equal to pi, and also R1 is in between 0 and R2. So here are the examples. Okay, now let's proceed to a polar rectangle. A polar rectangle is a simple polar region for which the bounding polar curve are circular arcs. For example, okay, this one shows the polar rectangle R given by, okay, this one is our R. Okay, R is in between 1.5 and also 2. Okay, the theta of R is in between pi over 6, this one, and also pi over 4. So this one is our A, and this one is our B. And this one is our R1, and this one is our R2. Now let's proceed to polar double integral. Okay, now let's say we have a surface Z, which is a function of R and theta. So this one is our region, which is mapped to Z. Okay, now we have this one and also this one, which is the theta. Okay, theta is equal to A for this one. For this line is theta is equal to B. This one is our R1, and also this one is our R2. So here is stated that if functions r theta is continuous on R and it has both positive and negative values, then the limit represent the net sign volume between the region R and also the surface Z. So the double integral of Z over R can be denoted by the polar Riemann sums, which is this one. If the surface is continuous and positive on R, then we can use the formula to calculate the volume. So this one is the formula, which is the double integral of polar coordinates. Okay, now let's evaluate polar double integrals. So this one is quite similar to rectangular coordinates. We have this equation. So this one, B and A is our theta. This one is our radius in terms of theta, where we convert our x and y into cos theta and also sin theta. Okay, now let's evaluate this region. Okay, for this one in the first quadrant. So here is theta is equal to 0, And this one is theta is equal to pi over 2. So next, we are going to find the value of r by drawing a line from the origin until the outer part. So here is our upper limit. This one is our lower limit. So our upper limit is equal to R2 and the lower limit is R1. So our R2 will be x square plus y square. Okay, now let's proceed to this figure. Okay, this one is the second quadrant. Means that our theta here is pi over 2. And this one is theta is equal to pi. So now let's draw the line from the origin. So here is the lower limit because it is close to the origin, and the upper limit which is far away from the origin. Here we need to find the value of R1, and this one is our value of R2. So for this one you can read on your own. Okay, now let's proceed to example 1. Evaluate double integral sine theta dA, where R is the region in the first quadrant, okay, that is outside the circle. R is equal to 2, and inside the quadrant, R is equal to 1 plus cos theta. Okay, so from here we can draw the circle first, okay, and then the circle, it is said that radius is equal to 2. Next, we draw the quadrant R. So we draw this one, and the R is 2, 1 plus cos theta. Okay, the region is in the first quadrant. So here is our first quadrant. Okay, but then it is said that it is outside the circle. Means that it is here. So now we are going to find the double integral of this region. Okay, now let me draw it back. We have this kind of region. Okay, this one is our theta is equal to pi over 2. This one is our theta is equal to 0. Now we are going to draw a line from the origin to the last one. Okay, this one is our lower limit. This one is our upper limit. Okay, our upper limit is 2, 1 plus cos theta. Okay, our lower limit is R is equal to 2. Okay, now let's write our equation. Okay, we have this one is A to B. Okay, pi over 2. This one is 0. And this one is our R1 and R2. Our R1 is 2, lower limit. R2 is our upper limit, which is 2, 1 plus cos theta. Okay, and then we take back this one. Sine theta R dr d theta. Okay, now we integrate this one first with respect to R. So this one is constant because we don't have R. So we just have to integrate this one. So we have pi over 2, 0. R square over 2. Okay, we write it back, sine theta. Okay, we put the limit. 2, 1 plus cos theta. And this one is 2 d theta. And now we are going to replace our R with this value. So we will have pi over 2, 0. Okay, from here we have pi over 2, 0. This one is 2, and also this one is 2. Okay, we put 2 outside. We have 1 plus cos theta square sin theta minus sin theta d theta. The next step is we integrate this one with respect to theta. Okay, now we are going to put the linearity. So we will have pi over 2, 0, 1 plus cos theta square sin theta d theta minus sin theta d theta. So from here we are going to have two equations. This one is our A, this one is our B. Okay, we integrate differently. So let's integrate part A first. Okay, so we have to let this one is equal to U. So U is equal to 1 plus cos theta. So we differentiate this one, we will get du over d theta is equal to negative sin theta. Then our du is equal to negative sin theta d theta. So from equation A, we have 1 plus cos theta square sin theta d theta. Okay, now we substitute plus cos theta is equal to u. Okay, this one is u square, and sin theta d theta is equal to negative du. Okay, now we can integrate this one. We will get negative u cubed over 3. Okay, now we substitute our u. We will get negative 1 plus cos theta cubed over 3. Okay, now we have this one. We integrate sin theta, we will get negative cos theta, and then this one will be positive because minus and minus. So this one limit pi over 2, 0. And then we substitute our limit inside theta. We will get 2 negative 1 over 3 minus negative 5 over 3. So the value is 8 over 3. Okay, now let's proceed to example 2. The sphere of radius A centered at the origin is expressed in rectangular coordinates. X square plus y square plus z square is equal to a square. And hence, its equation in cylindrical coordinates is r square plus z square is equal to a square. Use this equation and a polar double integral to find the volume of the sphere. The first step is find the value of theta, which is, this one is in between 0 and 2 pi. And then we need to find the R1 and also our R2. Now we are going to draw a line in order to find the R1 and also R2. Okay, so this one start from origin means that it is equal to 0. And our R2 is equal to A. Okay, this one. Okay, now we are going to find the function of the surface, which is in cylinder coordinates. This one, R square plus Z square is equal to A square. So our function will be Z is equal to A square minus R square. So this one is our surface. So we write the equation. We will have V is equal to 2 A square minus R square dA. Why it is 2 here? Because we need to find the volume of the sphere. This one is the hemisphere. Okay, then this one is equal to, okay, our limit theta 0 to pi. Okay, then our r, which is a 0, and then a square minus r square. Okay, we have 2 r dr d theta. And now we integrate with respect to r first, and then we will have this equation. Next, we substitute the value a to 0 inside this equation, and then we will get 2 pi to 0, 2 over 3 a cube d theta. Okay, now we are going to integrate this one. We will get 2 over 3 a cube theta 2 pi 0. Then we substitute the value of theta here, and then we will get 4 over 3 pi a cube. Okay, now let's proceed to find areas using polar double integral. So here is the formula for the area, the same as rectangular coordinate, so which is equal to r dr d theta. So the example 3, use a polar double integral to find the area enclosed by the 3 petal rows r equal to sine 3 theta. So we are going to calculate only one petal and we multiply by 3 because we have 3 petals. So here is our 3 petal. So we are going to use the petal in first quadrant. So here is our lower limit of the theta, and this one is the upper limit of the theta. So our lower limit of the theta is equal to 0, and the upper limit is theta is equal to pi over 3. So how to get this pi over 3? Because, okay, this one till this one we have pi, right? Okay, so this one, and also this one is similar. So that's why we divide by 3. Then our value of theta is in between 0 and pi over 3. And our r is in between 0 because it starts from the origin and to sine 3 theta. Substitute into this equation, we will have area is equal to, okay, theta 0 to pi over 3. This one is our r, 0 to sine 3 theta. Okay, and then r dr d theta. And don't forget, we have 3 petals, so we have to multiply 3 over there. And then we integrate with respect to r first. We will have 3 over 2 r square dr d theta. And then we substitute the value of r here. We will get okay, from here we can use cosine double angle formula, where sine square theta is equal to 1 minus cos 2 theta over 2. Okay, from here we will get 3 over 2 pi over 3 0 1 minus cos 6 theta over 2 d theta. Okay, we put 2 outside, so we will have 3 over 4 1 minus cos 6 theta d theta. And then we integrate this one, we will get 3 over 4 theta minus sine 6 theta over 6 pi over 3, 0. And then the final answer will be 1 over 4 pi. Okay, now let's proceed to triple integrals. So here is the definition of triple integral. Okay, to define the triple integral of function x, y, z over g, okay, this one is g. We first divide the boards into small boards, sub-boards by planes parallel to coordinate planes. So here we have sub-boards that contains any points outside the G, and choose an arbitrary point in each of the remaining sub-boards. Okay, this one is the properties of triple integral. Let's say we have constant C, and then we can move out C outside the integral, and this one will be like this. Okay, this one is first, second and third is equal. This one, let's say we have plus and minus, so we can split this one into two integrals. Okay, the last one, let's say we have this region and then it is divided by 2, and all of this region can be equal to G1 plus G2. Okay, next, let's evaluate triple integrals over rectangular boards. So here is the iterated integral of the triple integral. So dz is referred to L and K, dy, C and D, dx is A and B. So if you want to change this iterated, you can do, but with altering the order of integration too. Okay, now let's look at example 1. Evaluate the triple integral x, y, z square dv where b is the rectangular boards given by these limits. Okay, so we can use any of the 6 possible order of integration. Means that we can integrate with respect to x first, y and then z, or y first, z first and then x, and z first, then y, then x, and so on. So for this question, we want to solve it by integrate with respect to x first, and then y, and last one is z. Okay, so with respect to x first, we will get, okay, this one, it will be constant, so x square over 2. So we just write back y z square. Okay, and then we substitute the value, we will have this one, and then we integrate with respect to y. So for this one, we just write back z square, and then we integrate y over 2. So we will get y square over 4. And then we substitute the value, we left with 3z square over 4. And then we integrate this one, we will get z cubed over 4, which is equal to 27 over 4. Okay, this one is your exercise. Try to evaluate the triple integral. Okay, the answer is 6, 4, 8. Okay, you can try to do this.